There are questions that arrive with fireworks around them, and others that arrive more quietly, as if they had been waiting in the room for a very long time. The age of the universe belongs to the quieter kind. It does not announce itself with a launch countdown or a single dramatic image. It sits there instead as a patient fact to be earned, a number that can only be approached by following several kinds of evidence at once, evidence not all found in one place. It is inferred from light that has travelled almost the whole history of everything, from stars that burn slowly enough to keep their own clocks, from cooling embers of dead suns, from the way galaxies are spaced across immense distances, and from the simple but unsettling truth that the universe must always be older than the oldest things inside it. And tonight, we'll follow that evidence gently, one calm line at a time. Why, hello there, and welcome in. I'm Madeline Rowe, and tonight we're taking a slow, careful journey through one of the oldest questions in science: how we know the age of the universe. And if you enjoy calm, evidence-based science stories like this, please subscribe and come back for the next case file. Back in my office, the room has settled into that late-hour stillness that makes even a plain folder feel a little more important. A small desk lamp lays a warm circle of light across a folder marked with a plain label: the age of the universe. It is the kind of label that sounds simple until you try to answer it. And with that in mind, I settle into the chair, open the file, and begin where questions like this always begin. Not with one answer, but with the evidence. If someone asks how old a tree is, you might count rings. If someone asks how old a person is, you might ask for a birthday, or a record, or a memory. But the universe is not a tree, and there is no older clerk keeping its birth certificate in a safer drawer. There is no outside vantage point from which a witness can say, "Yes, I was there at the beginning. I saw the first light. I watched the first minute pass." The universe includes the clocks, the witnesses, the records, the light, the atoms, and the observers. So when astronomers say the universe is about 13.8 billion years old, what they mean is not that someone found a label attached to reality. What they mean is that several different physical processes, observed with great care, all point backward toward a hot early state and forward into a consistent timeline, and that the amount of time between that early state and now can be inferred with surprising precision. It helps at the beginning to notice that there are actually several age questions hiding inside the one large question. There is the age of the universe in the broad cosmological sense, the elapsed time since the early hot, dense phase described by the standard Big Bang model. There is the age of the oldest stars, which cannot be the same as the age of the universe, because stars had to form after the universe had already existed long enough for matter to cool and gather. There is the age of the oldest globular clusters, dense swarms of ancient stars in galactic halos. There is the age of white dwarfs, the cooling remains of once ordinary stars. There is the age of the elements inferred from radioactive decay. There is also the age of the universe at different redshifts, which is a subtler idea, not just how old the universe is now, but how old it was when the light from a distant galaxy first left that galaxy and began its long trip to us. That last question turns out to matter very much. So the file we are opening is not a single straight line. It is a set of overlapping routes that all attempt to answer the same question from different directions. One route begins with expansion. Another begins with stars. Another begins with the afterglow of the early universe, the cosmic microwave background. Another begins with radioactive clocks hidden in matter. Another asks a kind of legal consistency question. Could the universe, at some earlier redshift, have been younger than the objects already inside it? If the answer were yes, something in the cosmology would have gone wrong. And one of the quiet beauties of modern cosmology is that these lines of evidence, developed by different communities with different tools and different assumptions, do not wander off in random directions. They converge. Still, it is worth beginning with the roughest possible answer, because rough answers often teach the best instincts. The universe is expanding. Galaxies on the largest scales are receding from one another. The more distant a galaxy is, the faster that recession generally appears. Edwin Hubble did not discover the entire truth of cosmic expansion all by himself, and the story is richer than the short textbook version, but his name remains attached to the quantity that gives a first, almost naive estimate of cosmic age, the Hubble constant, written as h0 or h0. It tells us the current rate of expansion. If the universe had always expanded at exactly the rate it does now, and if you ran the film backward, you would get a rough age by taking 1 divided by h0. This is often called the Hubble time. That number is already suggestive. It says, in essence, if you know how fast the universe is stretching right now, you can estimate how long it would take for today's distances to have emerged from a much more compact state. It is a little like looking at an object drifting apart at a certain speed and guessing how long ago the pieces were closer together. The trouble, of course, is that the universe has not expanded at a fixed rate. Matter slows expansion because gravity pulls. Radiation mattered even more in the deep past. Dark energy in the late universe changes the story again by making expansion accelerate. So 1 over h0 is not the real answer. It is more like the first shape of the answer, the silhouette seen through frosted glass. That silhouette is still useful because it teaches one of the central instincts of the whole case. If you try to estimate age from the present expansion rate alone, you are doing something a little too simple, but not completely foolish. You are starting with the right quantity and leaving out the history. And history in cosmology is everything. A universe filled only with matter would expand differently from one filled with matter and dark energy. A universe with significant curvature would age differently from a flat one. A universe with unusual early physics could change the calibration of some of the tools we use later. So the age of the universe is not just the current speed of the cosmic film. It is the total shape of the cosmic film from early times until now. This is an important emotional turn in the story, because many people imagine the age of the universe as a direct readout from one modern instrument, when in truth it comes from reconstructing the universe's whole expansion history. To know the age, you do not only need the speed of the river today, you need to know how the river flowed earlier, when the banks were narrower, the current denser, the conditions different. Cosmologists describe this with a function, h of z, the expansion rate as a function of redshift. Redshift tells you how much the universe has stretched since light was emitted. Larger redshift means looking farther back. Once you know how expansion behaves across time, in principle, you can integrate backward and find the age. Even this phrasing, though, hides a choice. How do you know h of z? Sometimes you infer it within a model. Sometimes you measure pieces of it more directly. Sometimes you use standard rulers. Sometimes standard candles. Sometimes stellar clocks. Sometimes statistics from large samples of galaxies. So before the age of the universe becomes a number, it becomes a network of methods. One reason the modern answer feels so robust is that cosmology has learned to work like a patient detective rather than an impulsive one. It does not ask one witness for everything. It asks one witness for distance, another for timing, another for the early conditions, another for the late consequences, and then checks whether the testimonies fit together without too much strain. The age estimate that comes out of the cosmic microwave background, for example, is extraordinarily precise, but it is also model dependent. It is not that the microwave background has the age printed on it. It is that the background contains a very clean record of early universe physics, and if those physics are interpreted within the standard cosmological model, the age follows. Stellar ages, on the other hand, are less direct as cosmological measurements, but more independent of early universe assumptions. They ask a different question. How old are the oldest things we can see that formed out of ordinary matter and spent billions of years evolving according to stellar physics? If those ages come out wildly inconsistent with the CMB-based age, something would be wrong. But they do not come out wildly inconsistent. They come out reassuringly close. So the first true chapter of the case is this. A useful rough age comes from the present expansion rate, but the real age comes from the full history of expansion. And the full history of expansion has to be reconstructed from several kinds of evidence. That reconstruction is where the story becomes interesting. It is useful here to linger for a moment with a simple thought experiment. Imagine 3 universes that happen to share the same Hubble constant today. In one, matter dominates almost all the way through, forever tugging against the expansion. In another, dark energy begins to dominate late, easing the deceleration and then turning it into acceleration. In a third, something exotic briefly changes the expansion early on and then fades away. All 3 could, in principle, have the same present-day expansion rate, and yet not be the same age. That is because age depends on the whole accumulated history, not merely the final line in the ledger. Cosmology is full of such lessons. The present is rarely enough by itself. This is also a good place to clear away one common confusion. The age of the universe is not the same thing as the size of the observable universe. People sometimes assume that if the universe is about 13.8 billion years old, then the most distant things we can see must be 13.8 billion light years away. But space has been expanding while the light travelled. So the present-day distance to the edge of the observable universe is much larger than 13.8 billion light-years. Age is a time. Observable radius is a distance. They are related, but not interchangeable. This matters because the age question can sound simpler than it is. Even the phrase, "how far back we see," is tangled up with how expansion stretches space while light is en route. Imagine, for a moment, the universe in its first few 100,000 years. Not a universe of stars and galaxies, because those do not exist yet. Not a universe of transparent space, because light is not yet free to travel very far. Instead, think of a hot plasma, a dense mixture of photons, electrons, and baryonic matter, with dark matter shaping the gravitational scaffolding in the background. In that early plasma, density variations existed. Some regions were slightly denser than average, some slightly less dense. Gravity tried to compress the denser regions further. Radiation pressure pushed back. The result was not quiet collapse, but oscillation, a cosmic ringing, sound waves moving through the early universe. This is one of those facts that sounds almost decorative until you realise how important it is. The early universe really did support acoustic oscillations. It had pressure, it had inertia, it had regions trying to fall inward and pressure trying to restore them outward. These sound waves did not move through air, of course. They moved through the hot photon-baryon fluid. And because physics was the same everywhere, those waves followed rules we can calculate with remarkable confidence. Then came recombination, a word that sounds more complicated than the event feels. The universe cooled enough for electrons and protons to combine into neutral hydrogen. Once that happened, photons no longer scattered constantly off free electrons. Space became transparent. Light could travel freely. The radiation released from that surface of last scattering is what we observe today as the cosmic microwave background, stretched by expansion into microwave wavelengths. When we map the tiny temperature fluctuations in that background, we are looking at a snapshot of the universe when it was only about 380,000 years old. If you like, you can imagine the early universe as a room full of curtains in a hard wind. Before recombination, the curtains are constantly touching, pulling, and pushing, so motion does not travel very far before being redistributed. After recombination, the curtains separate, and what remains is the pattern they had at that last common moment. The cosmic microwave background is not the beginning itself. It is the earliest light we can directly observe, the oldest visible record. It is a kind of official photograph, taken not at the birth of the cosmos, but very early in its childhood, before stars, before galaxies, before planets, before anything we would recognize as a familiar place. Now here is the part that matters for age. Those acoustic oscillations left behind a characteristic scale, the sound horizon, the maximum distance a sound wave could have traveled in the early plasma before recombination. That scale is imprinted on the CMB as a preferred angular size. It is also imprinted later in the distribution of galaxies as a preferred separation scale, which we will come to in a while. The crucial point is that the CMB measures the acoustic structure with astonishing precision. The angular size of that acoustic scale is one of the cleanest pieces of information in all of observational cosmology. But notice the subtlety. What the CMB gives you directly is not a simple label saying age equals this. It gives you a set of precisely measured patterns, peak positions, peak heights, polarization information, lensing information, and more. To turn those into an age, you place them inside a cosmological model, usually the base lambda cold dark matter model, spatially flat, with dark matter, ordinary matter, radiation, and dark energy in the form of a cosmological constant. Within that framework, the same parameters that explain the acoustic peaks also imply a present expansion rate, a matter density, a baryon density, a scalar spectral index, and a cosmic age. The model is doing real work here. It is a physically motivated framework, heavily tested and impressively successful, but it remains a framework. This distinction matters because some discussions of cosmology become less clear than they need to be. The cosmic microwave background does not directly photograph a date stamp. It constrains parameters with extraordinary precision, and from those parameters, under the standard model, we infer an age. That inferred age, in the Planck era, sits very close to 13.8 billion years. Older missions like WMAP arrived at very similar ages, though less tightly constrained, which is itself comforting. Different generations of increasingly precise CMB data did not produce entirely different stories. They sharpened the same one. There is something almost architectural about this. The CMB gives you the blueprint of the early universe, not only the rough outline. The heights and positions of the acoustic peaks depend on physical matter density, baryon density, the geometry of space, the amount of dark matter, and the time available before recombination. Once those are jointly constrained, the age of the universe emerges as part of a coherent structure. It is like measuring the span of an arch, the angle of the stones, the thickness of the supports, and the distribution of weight, and then finding that the whole building implies a single, consistent shape. The geometry deserves a little more attention than it usually gets in popular retellings, because geometry is one of the quiet ways age sneaks into the story. In a spatially flat universe, the relation between the physical scale of the sound horizon and its observed angular size takes one form. In a curved universe, open or closed, that relation shifts. This creates degeneracies. You could change geometry and compensate elsewhere, preserving some observables while affecting others. This is one reason why CMB data alone, though powerful, is not always enough to pin down every cosmological quantity independently. Additional probes, especially baryon acoustic oscillations, help break the geometric degeneracy. And once that degeneracy is broken, the age settles into place more firmly. This is why the CMB became such a decisive player in modern cosmology. Earlier age arguments often relied on one class of astrophysical object or another. Those arguments were useful, and in some cases prescient, but they carried larger uncertainties and more room for disagreement. The CMB, by contrast, gave cosmology a common reference frame. It said, here is the early universe in a form that can be mapped across the entire sky. Here are the fluctuations from which later structure grew. Here is the acoustic information that calibrates the large-scale geometry. Once this record existed in detail, the cosmic age stopped being mainly a matter of broad plausibility and became a matter of precision inference. And yet, precisely because the CMB-based age is model-dependent, responsible astronomers do not stop there. They ask whether later universe evidence agrees. If the age inferred from the CMB in the standard model were 13.8 billion years, but the oldest stellar populations clearly came out older than that by a wide margin, then the model, or the stellar physics, or both, would be under strain. In the late 20th century, something like this worry briefly existed. It was sometimes called an age crisis. Under older cosmological assumptions, the universe could appear younger than some of its oldest stars or clusters. The discovery that cosmic expansion is accelerating, and thus that dark energy plays a major role, changed the bookkeeping. A universe with dark energy can be older for a given present-day expansion rate than a simple matter-only universe. In a way, acceleration gave the universe back some time. That acceleration deserves a fuller visit because it is one of the quiet heroes of the age story. When distant Type 1a supernovae were used in the late 1990s to trace the expansion history, the result was not what many expected. Instead of a universe whose expansion was slowing under gravity in a simple way, the observations indicated that the expansion had been accelerating at late times. In ordinary language, the universe was not merely coasting outward. The large-scale expansion was picking up. Within the standard interpretation, this meant some form of dark energy, most simply Einstein's cosmological constant, had come to dominate the late-time dynamics. Why does that help the age problem? Because a universe that spent more time decelerating strongly under matter alone would, for a given Hubble constant today, generally be younger. A universe with late-time acceleration can be older. The reason is not mysterious once you sit with it. The expansion history changes. The route from the early hot state to the present stretches differently. This was one reason the old tension between stellar ages and cosmological ages softened so dramatically once dark energy entered the standard picture. You could say that dark energy changed the tone of cosmic aging. A matter-only universe spends more of its history being held back. a dark energy universe eventually enters a gentler but more accelerated late-time expansion. The timeline lengthens enough to fit the oldest stellar systems more comfortably. So supernova cosmology, though not usually presented as an age method first, is part of why the age answer now feels coherent. This is where baryon acoustic oscillations enter the story, carrying the echo of the same sound waves that shaped the CMB. If the CMB gives us the early universe record of the sound horizon, BAO gives us its later universe footprint. The picture is beautiful once you slow down enough to hold it. In the early universe, a density perturbation launches a pressure wave outward through the photon baryon fluid. Dark matter remains concentrated near the center because it does not feel radiation pressure in the same way. When recombination happens and the radiation decouples, the outward moving shell effectively stalls. The result, long after galaxies form, is a slight preference for matter to be separated by a characteristic co-moving scale, roughly 150 megaparsecs. In galaxy surveys, this shows up as a subtle bump in the correlation function, or wiggles in the power spectrum. Not a loud signal, a statistical one, but a very useful one. BAO is called a standard ruler because the scale is set by early universe physics and can be calibrated. Once you have that ruler, you can ask how large it looks on the sky at different redshifts, and how much redshift interval corresponds to its radial extent. Those observations constrain angular diameter distances and h of z. In other words, BAO tells you about the expansion history after the universe has become transparent and structured. It does not replace the CMB, it complements it. There are a few ways to use BAO in the age story. One way is to calibrate the ruler with the CMB sound horizon, and then infer late universe distances and expansion. Another is to use Big Bang nucleosynthesis information for the baryon density, together with the robustly measured acoustic angular scale, creating what is sometimes called an inverse distance ladder. This is an elegant phrase. In the classical distance ladder, you work outward from nearby calibrated objects. In the inverse ladder, you begin with early universe or early physics calibration and work inward through the large-scale structure of the later universe. DESI is now providing exceptionally precise BAO measurements across a wide redshift range, and these measurements are reinforcing a value of H0 that sits near the CMB-based value rather than the higher end favoured by local distance ladder measurements. That matters for age, because a lower H0 generally corresponds, all else being equal, to an older universe. Still, BAO also teaches something more conceptual. It reminds us that the age of the universe is not only about clocks, it is also about rulers. If you know how expansion stretches a standard ruler across redshift, you gain access to the geometry of cosmic history. And geometry in cosmology is time in another language. Distances, rates, densities, and age are all tied together. Before we leave the expansion side of the file, it is worth pausing on the Hubble time again, because it helps develop intuition about why different values of H0 create such strong feelings in cosmology. If the current expansion rate is higher, the naive Hubble time is shorter. If the rate is lower, the naive time is longer. Once you include the full expansion history, the relationship is no longer just 1 over H0, but the instinct remains. A universe expanding faster today tends to be harder to make old enough, especially if you want it to remain consistent with ancient stars, globular clusters, and high redshift objects. This is one reason the Hubble tension matters even to people who are not primarily interested in H0 itself. It is not just about a disagreement over one number, it presses on the overall timeline. There is a special calm in realizing that age, distance, and expansion cannot really be pried apart. We speak as if one method measures distance, another measures expansion, another measures age. But at the deepest level, each is telling us something about the same unfolding history. The universe is not giving separate answers to separate clocks. It is giving many partial answers to the same long question. Now we can move to methods that feel less geometric and more intimate. Instead of looking at the universe as a whole, we look at stellar populations that have been sitting quietly for an immense span of time. Here, the first great witnesses are globular clusters. A globular cluster is one of the oldest and most dignified things in a galaxy. It is a dense, gravitationally bound swarm of stars, often very old, often orbiting in the halo rather than the disk. These clusters are not merely pretty ornaments, they are fossil systems, many formed early in galactic history. If you can determine the age of the oldest globular clusters, you immediately get a lower limit on the age of the universe. The universe has to be at least older than they are, plus however much time was required before they formed. How do you age date a globular cluster? The classic method relies on the color magnitude diagram, a kind of census plot in which stars are placed according to brightness and color. Stars do not remain fixed on this diagram. They move through life according to mass and composition. In a cluster, the stars are usually assumed to have formed at roughly the same time, which means the present distribution of stars across the diagram preserves a record of how long they have been evolving. The most famous diagnostic feature is the main sequence turn-off. Stars spend most of their lifetimes on the main sequence, burning hydrogen in their cores. The more massive stars burn faster and leave first. So the location of the turn-off, the point where stars peel away from the main sequence, acts as an age indicator. A cluster whose turn-off occurs at lower mass and lower luminosity is older, because more time has passed for progressively smaller stars to exhaust core hydrogen. To appreciate why this works, it helps to think of a cluster not as a pile of individual biographies, but as a single family portrait taken late in life. The massive stars, bright and impatient, are the ones who have already left the room. The stars still sitting along the main sequence are the ones with more modest masses and longer burning reserves. If you know stellar physics well enough, the location where the portrait begins to thin out tells you how much time has passed since the family assembled. It is one of the gentlest clocks in astrophysics. This is already powerful, but modern work goes further. Instead of using only the turn-off, astronomers can fit the full color magnitude diagram, bringing in metallicity, helium abundance, reddening, distance, and alpha element enhancement in a more careful statistical framework. That matters because cluster ages are sensitive to these quantities, and the more honestly you account for them, the more credible the final age becomes. Recent work using Gaia distances and hierarchical modelling has pushed this approach to impressive precision, finding that the oldest globular clusters are about 13.4 billion years old. From those cluster ages, with a reasonable allowance for the time between the Big Bang and cluster formation, one can infer a universe age around 13.6 billion years, with upper limits that remain very comfortable beside the standard CMB result. There is something satisfying about that agreement because the methods are so different. The CMB age depends on interpreting an early universe radiation field within a cosmological model. Globular cluster ages depend on stellar evolution, population modelling, distances, extinction corrections, and careful statistics on resolved stars. When these point to compatible ages, confidence deepens, not certainty in a metaphysical sense, but confidence in the way many good sciences acquire it, by convergence. The cluster story also teaches patience. Globular clusters do not give the age of the universe all by themselves. They give the age of their oldest stars or stellar populations. One must then account for the time between the Big Bang and the formation of those stars. That gap is not enormous on a 13 billion year scale, but it is not zero. Stars did not form at the first instant. Matter had to cool. Small perturbations had to grow. Gas had to collect into dark matter halos. The first generations of stars had to begin. So when the oldest cluster ages are converted into a cosmological age, there is a formation time correction in the background. That correction is part of the honesty of the method. It is also worth remembering that globular clusters once played a more combative role in cosmology than they do now. There were periods when their inferred ages seemed uncomfortably close to, or even older than, cosmological ages derived under simpler assumptions. That tension forced astronomers to look more carefully at both stellar models and cosmological models. Better distances, better opacities, better compositions, better treatment of helium and dust, and a better cosmology all helped. In hindsight, the argument was healthy. It showed that age is not a decorative number, it is a constraint with teeth. Closely related to globular cluster dating, but distinct enough to deserve its own room in the office, is white dwarf cooling. White dwarfs are the final state of ordinary stars like the Sun, though the Sun itself has not yet reached that stage and will not for a very long time. A white dwarf is not powered by ongoing fusion. It is the hot remnant core left after the outer layers are shed. Once formed, it simply cools. Slowly, yes, but steadily. That makes white dwarfs useful clocks. If you examine a population of white dwarfs in a cluster, you can look at the cooling sequence, the distribution of white dwarfs by brightness and colour. Younger white dwarfs are hotter and brighter. Older ones are cooler and fainter. Over immense spans of time, the faint end of the cooling sequence builds up, and the luminosity function changes in characteristic ways. By comparing the observed cooling sequence with theoretical models, astronomers can estimate the cluster's age. This method is attractive because it rests on different physics than the main sequence turnoff. The turnoff asks how long stars take to exhaust hydrogen in their cores. White dwarf cooling asks how quickly stellar remnants radiate away stored heat. If both methods agree, confidence rises again. In the globular cluster, 47 Tucani, recent JWST, work on the white dwarf cooling sequence has found an age of about 11.8 billion years, in agreement with main sequence turn-off ages and eclipsing binary constraints for that cluster. Now, 47 Tuc is not one of the absolute oldest clusters in the Milky Way, so its age is not meant to equal the age of the universe. That is not the point. The point is that this independent stellar clock confirms the broader story. Ancient clusters are indeed ancient. The stellar clocks are internally coherent. White dwarf clocks are especially comforting because they are based on fading rather than fuel. A white dwarf does not hide extra reserves in the way active stellar evolution sometimes seems to. Once the remnant is formed, the logic is simple. It cools. The details matter, of course. Crystallization, interior composition, atmospheric properties, and dynamical selection effects all matter. But the basic moral remains plain. Some clocks in the universe work by burning, others work by cooling. Both kinds point toward deep time. White dwarfs also have a certain poetic usefulness in sleep science. They are stars that no longer pretend to be busy. They have finished the loud part and entered the long cooling. In a cosmological episode, that tone matters. We are not only studying explosions and births, we are studying leftovers, embers, slow fades, and what those slow fades can tell us about the age of everything. There is an even older style of timekeeping in the file, and it comes from radioactive elements. Long before precision cosmology could lean on full-sky microwave maps, astronomers and physicists were already trying to estimate the age of the galaxy, and by extension to set lower bounds on the age of the universe using nuclear chronometers. The principle is familiar from radiometric dating on Earth. Unstable isotopes decay at known rates. If you know or can estimate production ratios and measure present abundances, you can infer timescales. In the galactic context, long-lived isotopes of thorium and uranium have been especially important. This method is not as crisp in practice as one might wish. The complication is not the decay law itself, which is beautifully simple, but the astrophysical history. You must understand where the isotopes were produced, in what ratios, through what nucleosynthetic channels, and how galactic chemical evolution altered the mixture over time. That introduces uncertainties. Even so, nucleocosmochronology played an important historical role by showing that the galaxy must be old, on the order of many billions of years. Late 20th century summaries found firm lower bounds around 9 to 10 billion years, and more model-dependent galactic ages around roughly 12.8 billion years, consistent with globular-cluster and white-dwarf dating. These numbers were not final answers, but they were useful guide rails. They told cosmology not to become absurdly young. If globular clusters and white dwarfs feel like ancient household clocks, nuclear chronometers feel like watches found in the walls. They are less straightforward to read, perhaps, but they carry the same implication. Deep time is real, and the universe must allow enough of it. There is another class of stellar age argument that is worth a few quiet pages, because it fills in the picture between whole clusters and dead stellar remnants. Astronomers also study individual very old stars, especially metal-poor stars in the halo of the Milky Way. Low metallicity often suggests extreme age, not because metal-poor automatically means oldest in a simple one-to-one way, but because such stars formed before many generations of stellar enrichment had seeded the interstellar medium with heavier elements. Some of these stars are relics of the early Milky Way, or of smaller systems later accreted into it. By modelling their temperatures, luminosities, compositions, and evolutionary states, one can estimate ages that again push close to the age of the universe. Individual stellar ages are often less clean than cluster ages, because you lose the powerful shared formation assumption of a cluster population. But they matter because they confirm the general theme. The oldest ordinary stars are not 7 billion years old or 9 billion years old. They are astonishingly ancient. They are part of a galaxy whose oldest components formed when the universe itself was still young. Once more, the stellar evidence does not rebel against the cosmological timeline. It fits inside it. Now we come to a method that has become increasingly important because it links cosmic expansion directly to galaxy aging: cosmic chronometers. This is one of my favourite ideas in the whole file because it is both elegant and modest. It does not claim to solve everything. It simply says this: if you can identify passively evolving galaxies whose stellar populations formed early and then aged quietly, you can use differences in age between such galaxies at slightly different redshifts to estimate the expansion rate. The key relation is conceptually simple, even if the practical work is demanding. The Hubble parameter at redshift z is related to the derivative dz over dt, the change in redshift with cosmic time. So if you can estimate a small age difference between populations of old galaxies at nearby redshifts, you can infer h of z directly, or at least more directly than with many other methods. In practice, this requires selecting massive, passively evolving galaxies, obtaining high-quality spectra, estimating stellar ages from those spectra, and controlling systematic effects with care. It is not easy, but it is powerful because it does not rely on the sound horizon in the same way CMB and BAO methods do. The cosmic chronometer approach therefore occupies a fascinating middle ground. It is still tied to astrophysical modelling of stellar populations, so it is not assumption-free. Nothing in astronomy really is, but it offers a comparatively direct way to access the expansion history at late times. And once again, because age depends on the full expansion history, any good handle on h of z is part of the age story. The beauty of the method lies in how little it asks conceptually. It does not need a standard candle whose absolute luminosity must be calibrated through several rungs. It does not need the sound horizon as a ruler. It asks only for old galaxies that have been evolving quietly enough to function as differential clocks. It compares one redshift slice to another and asks how much time elapsed between them. In a universe full of messy astrophysics, this relative approach has a certain wisdom. It does not demand perfection from galaxy age dating. It demands controlled differences. This is why some modern discussions of the Hubble tension separate sound horizon-based methods, distance ladder methods, and so-called one-step methods. Cosmic chronometers belong among the latter class of probes that try to reach h0 or h of z without relying on the local distance ladder or the CMB sound horizon in the usual way. When compilations of such methods are gathered together, their preferred h0 values often sit closer to the lower, Planck-like range than to the higher local ladder range. This does not end the debate, but it adds texture. The disagreement may not be a neat early versus late split. It may instead reflect a deeper distinction between ladder-based methods and a broader set of one-step or non-ladder probes. This matters for the age file, because if many non-ladder methods cluster around a lower h0, the implied age of the universe becomes easier to reconcile with stellar ages and other late-time clocks. If, by contrast, the highest local h0 values are ultimately confirmed and made fully consistent with everything else, then cosmology may need some compensating change in the early or late expansion history, or both, to preserve the age budget. There is another powerful age-based check, and it is wonderfully unforgiving. The universe at any redshift must be older than the oldest objects it contains at that redshift. That sounds almost childish in its obviousness, but obvious constraints are often the most useful. If you can identify galaxies or quasars at moderate or high redshift whose inferred ages are substantial, then the cosmological model must provide enough age by that redshift to accommodate them. If not, the model is in trouble. This is the logic behind work on old astrophysical objects across redshift. By constructing age-redshift diagrams using old galaxies and distant quasars, one can derive upper limits on h0 under a chosen late-time cosmological model. The reason is intuitive. The age of the universe at any redshift scales inversely with the expansion rate normalization. If h0 is too high, the whole universe becomes too young, not only now, but at earlier epochs as well. Then you risk the paradox of a universe younger than its contents. Recent studies using old astrophysical objects up to redshift around 8 find, under late-time lambda, cold dark matter assumptions, a 95% upper limit on h0 below about 73.2 kilometers per second per megaparsec. That is an interesting boundary because it brushes against the higher local measurements. The result is not a magical verdict because it depends on the reliability of object age estimates and on assumptions about incubation time. the interval between the Big Bang and the formation of the object in question. But it is a valuable consistency test. It says, in effect, do not spend cosmic time too casually. There are already old things in the early universe that need room to have existed. Incubation time deserves a moment of quiet attention because it prevents sloppy storytelling. Suppose you observe an old galaxy at some redshift and infer a stellar age of 1 billion years. That does not mean the universe at that redshift was exactly 1 billion years old. It must have been older than that, because the galaxy had to form after the Big Bang. The difference between the age of the universe at that redshift and the age of the object is the time it took for the relevant matter to collapse, cool, and form stars. That is the incubation time. In many applications, it is on the order of a few 100 million years. Small compared with 13.8 billion years. Not small enough to ignore imprecise arguments. These old object arguments also produce a certain emotional effect that is different from the CMB or BAO. The microwave background is a global fossil. BAO is a statistical feature spread across millions of galaxies. But an ancient galaxy at high redshift, or an early quasar already surprisingly mature, feels personal. It is one object standing in the doorway of the early universe saying, I am already here, and I have already been here a while. That makes the age constraint vivid in a way formulas do not. At this point in the file, the room is getting comfortably full. We have the CMB and the early acoustic scale. We have BAO as the late echo of that acoustic physics. We have cosmic chronometers from passively evolving galaxies. We have globular-cluster ages from full color magnitude diagrams. We have white-dwarf cooling sequences. We have nuclear chronometers. We have old astrophysical objects acting as consistency constraints at redshift. Each method has its own personality, its own systematics, its own strengths, and its own ways of failing. But they are not contradicting one another in some chaotic fashion. They are circling a common timeline. It may be helpful now to pause and distinguish precision from independence. The CMB within base lambda, cold dark matter, gives the sharpest single age estimate. It is extraordinarily precise, but it is also a model-dependent inference. Globular clusters and white dwarfs provide ages that are in some sense more local and more independent of early universe assumptions, but they generally carry larger systematic uncertainties. Cosmic chronometers access h of z more directly at late times, but depend on stellar population modelling and careful selection. Old object constraints are powerful in principle, but delicate in practice because age estimates at high redshift can be challenging. None of this weakens the case. It clarifies it. Robust knowledge does not require that every method be equally precise or equally direct. It requires that their limitations be different enough that agreement becomes meaningful. This is one reason the age question is more satisfying than some cosmological questions. On the surface, the age of the universe sounds like a single number, perhaps boring in its finality. But in practice, it is a meeting point between different realms of physics. Atomic transitions, nuclear decay, stellar interiors, radiative transfer, large-scale structure, gravitational growth, and relativistic cosmology. It is a number, yes, but it is a number supported by a federation of evidence. That federation did not always look so calm. There was a time when the oldest stars and clusters seemed uncomfortably old compared with the age implied by simpler cosmological models. This so-called age tension was among the reasons the late 20th century cosmological picture felt incomplete. The eventual discovery that expansion is accelerating, and thus that dark energy is part of the cosmic budget, changed the age calculation. a universe dominated at late times by a cosmological constant expands differently from a matter-only universe. Given the same Hubble constant, it can be older. The age crisis eased, the timeline began to align, and yet cosmology never stays still for long. The age tension receded, but the Hubble tension emerged. Here we should be careful, because this part of the case file can easily become sharper and louder than the rest, and the tone of the room is not sharp tonight. The Hubble tension refers to the disagreement between lower H0 values inferred from early universe data, especially the Planck CMB, interpreted within base lambda, cold dark matter, and higher H0 values measured using the local distance ladder, especially Cepheids and Type 1 A supernovae in the SH0ES program. The difference is not tiny. It is large enough to have sustained years of discussion, proposed solutions, new physics models, and renewed scrutiny of systematics. Why does that matter for the age of the universe? Because changing H0 changes the age budget. In the simplest intuition, raising H0 tends to shorten the age of the universe. But the real situation is subtler, because one can also modify the pre-recombination sound horizon, alter dark energy behavior, adjust curvature, or introduce other changes that can preserve some observables while shifting others. This is why the Hubble tension is not merely a fight over the current expansion rate. It is a pressure test on the coherence of the entire timeline. Some proposed solutions attempt to change early universe physics before recombination. Early dark energy is the most famous class. The idea is to increase the expansion rate before recombination, shrinking the sound horizon so that the same observed acoustic angular scale can be reconciled with a higher H0 today. Clever, yes, but difficult. Such models must not only shift the sound horizon, they must also fit the rest of the CMB data, BAO, supernovae, structure growth, and other observations. Many proposals help one tension while straining another. Cosmology is not fond of free lunches. This is why age-based evidence remains useful in the Hubble tension era. Globular clusters and old astrophysical objects do not single-handedly adjudicate the debate, but they do constrain the space of acceptable stories. If one tries to push H0 high while leaving the late-time age-redshift relation too compressed, old stars and ancient objects begin to object. They do not necessarily slam the door, they lean against it. There is a particularly interesting argument in some recent meta-analyses of H0 measurements independent of the CMB sound horizon. Rather than seeing the full tension as simply early versus late, these analyses split non-sound horizon measurements into distance ladder methods and one-step methods. The distance ladder compilation centers high, around the low 70s. The one-step compilation, which includes cosmic chronometers, strong lensing, megamasers, gamma-ray attenuation, and other methods, tends to center lower, closer to the high 60s. Remove a couple of outliers, and the one-step estimate drops even more neatly toward the Planck range. If that picture survives further scrutiny, it may suggest that the real divide is not early versus late in the broadest sense, but distance ladder versus much of everything else. I would not want to oversell that as settled truth. Meta-analyses depend on choices about inclusion, independence, and systematics, but it is an illuminating way to think. The age of the universe may be telling us not that one side of cosmology is completely wrong, but that some methods may be more entangled with particular assumptions or systematics than others. If so, the age story becomes part of a wider project, sorting which probes agree not only numerically, but structurally. There is another thread that quietly strengthens the whole picture, and that is the age of the universe at specific moments, not merely now. Cosmologists often ask how old the universe was when recombination happened, when the first stars likely formed, when the earliest galaxies assembled, when the Sun formed, when Earth formed, when the first globular clusters settled into the halo. These are not separate universes. They are timestamps within one continuous history. Once the age-redshift relation is known, these timestamps can be placed consistently. The universe at recombination was only hundreds of thousands of years old. The first stars likely formed within the first few 100 million years. By about 1 billion years, the universe already hosted surprisingly mature structures. By the time the Sun formed, the universe was already well into middle age, enriched by many earlier generations of stars. This layered timing matters because it shows that age is not just an endpoint. It is a timeline populated with events whose ordering and spacing also make sense. Sometimes this is the most persuasive way to feel the age answer, not as a single final number, but as a set of intervals that fit. There is enough time for primordial nucleosynthesis in the opening minutes, enough time for recombination in the first few 100,000 years, enough time for gravitational structure to grow, enough time for the first stars and galaxies, enough time for globular clusters to become old, enough time for white dwarfs to cool, enough time for the Milky Way to assemble, enough time for the Sun and Earth to arrive late in the story, enough time for life to appear on one small world, and, much later, ask how long the whole thing has been going on. Let me slow the pace even further and ask a question that tends to get lost when people talk about age as a final number. What does it really mean to say the universe is 13.8 billion years old? It does not mean that there is some external universal clock against which the cosmos has been ticking in a human-like way. Cosmic time in the standard cosmological model is the proper time measured by observers co-moving with the overall expansion, those who move with the average flow of matter on large scales. In an inhomogeneous universe full of local motions and gravitational wells, this is already an idealization. A powerful one, but still an idealization. The age is therefore not an ordinary age in the sense of a person's age. It is the integrated duration along the cosmological flow from the hot early state to now. This sounds abstract, but it matters because it explains why the number can be so meaningful and yet so model-bound. If you accept the large-scale homogeneity and isotropy of the standard cosmological framework and the set of parameters that best fits the data, then the cosmic age is well-defined and sharply constrained. If you radically change the framework, the meaning of the number can shift. But the reason the standard answer carries authority is precisely that so many different lines of evidence support the framework in which the number is calculated. The universe's age is therefore not a guess. It is not a vibe. It is not a piece of numerology. It is a consequence of a well-tested expansion history, cross-checked by ancient stellar systems and late-time astrophysical clocks. The formal precision on the CMB-derived age is much tighter than the precision on stellar ages, but the stellar ages are not random broad smudges. They are good enough to say yes, the oldest globular clusters are ancient enough to support a universe of roughly this age. And no, the timeline is not being stretched into nonsense. There is also a human satisfaction in the fact that some of the quietest objects in the sky contribute so strongly to this answer. Globular clusters do not explode for our benefit. White dwarfs do not advertise. Passive galaxies do not perform dramatic acts. They simply keep aging. In a field often associated in the public imagination with violent events, the age of the universe is pinned down in large part by objects whose main achievement is endurance. You can feel that endurance if you picture a globular cluster hanging in the halo of the Milky Way, dense and old, full of stars that formed when the galaxy itself was young. You can feel it in a white dwarf radiating stored heat into darkness over billions of years. You can feel it in the slight but measurable aging difference between populations of old galaxies separated by a little redshift. You can feel it in radioactive nuclei that have been decaying since before the sun existed. Each is a different kind of patience. Cosmology, in this sense, is the science of patient witnesses. There is one more subtle point worth including before the closing stretch. The age of the universe is sometimes spoken of as though it were only interesting because it is ancient, but its true importance is structural. The age participates in many consistency relations. It affects when the first stars could form, how long galaxies had to assemble, how much time stellar populations had to enrich themselves with heavier elements, whether high redshift quasars can plausibly have grown as large as they did, and how late-time objects fit within early-time cosmology. Age is not just a number on the wall, it is the time available for every other process in the cosmic house. This is why, for instance, the existence of extremely massive quasars at very high redshift has sometimes sharpened age conversations. If the universe is not old enough by a certain redshift, then black holes of a certain inferred mass become difficult to grow by ordinary accretion histories. If galaxies appear surprisingly mature very early, one asks again whether there was enough time. Such arguments are often messier than headlines suggest, because the astrophysical pathways can be uncertain. But the principle remains. Time is a resource, and cosmology must allocate it honestly. There is also the question of what future methods may add to the case. Standard sirens, for example, gravitational wave events whose distances can be inferred from the waveform itself, promise an independent route to expansion measurements. They are not yet the dominant method in the age story, but they may become important. Unlike some traditional methods, standard sirens do not rely on a cosmic distance ladder in the same way. If they eventually provide a clean measure of H0 and the expansion history, they will feed directly into age arguments. I like the thought of that. Even the universe's ripples in space-time may soon take a seat in this office and offer testimony. Likewise, future galaxy surveys, deeper JWST observations, better stellar models, and improved parallax distances will continue to refine the slower clocks. The file is not closed in the sense of no further work remaining. It is closed in the more satisfying sense that the main answer is secure enough for refinements to be interesting rather than destabilizing. That is a good place for a science to be. The current standard picture allocates time well. The age of the universe, around 13.8 billion years, is old enough for globular clusters, near 13.4 billion years. Old enough for white dwarf cooling ages in ancient clusters. Old enough for the growth histories we broadly infer, and consistent with a large suite of observations from the early to the late universe. There are tensions, yes. The Hubble tension is real enough as a research problem. Some late-time large-scale structure measurements pull a little low in clustering amplitude compared with Planck. Some dark energy fits acquire interesting hints when one allows extra freedom. But these are not signs that the age estimate is floating unmoored. They are signs that the baseline framework is good enough for remaining discrepancies to matter. Sometimes the healthiest way to understand a scientific problem is not to ask whether the whole picture is wrong, but whether the picture is good enough that the residual mismatches point to something small but important. That is where cosmology may now stand. The age of the universe is not an open wound. It is more like a well-healed bone that still aches faintly when the weather changes, reminding us that even strong structures carry traces of older stress. In my office, this is usually the moment when the folder begins to look less like a mystery and more like a map. The label has not changed. The room has not changed. The lamp is still warm, but the paper inside now connects. Expansion rate acoustic scale, standard ruler, supernova dimming, colour magnitude diagram, turn-off, white dwarf cooling, radioactive decay, redshift age relation, old galaxies, high redshift quasars. They are no longer separate phrases, they are joined into a timeline. If you wanted the shortest honest summary, it might be this. We know the universe's age by measuring how the universe expands, by reading the physical record left in the cosmic microwave background, by tracing the later echo of that record in baryon acoustic oscillations, and by checking the result against independent clocks carried by the oldest stars, globular clusters, white dwarfs, radioactive elements, and ancient astrophysical objects. No single method stands alone. Together, they form one of the strongest convergent stories in science. And if you wanted the gentle version of the same summary, the one suitable for a darker room and a softer hour, it might sound like this instead. The universe has been leaving timestamps everywhere. Some are written in light from when it was very young. Some are written in the slow aging of stars. Some are written in the cooling of white dwarfs. Some are written in the spacing of galaxies across immense volumes. Some are written in unstable nuclei that have been ticking quietly for eons. We do not know the age because one witness told us. We know it because the witnesses, taken together, are difficult to ignore. There will probably always be refinements, better stellar models, better Gaia distances, better white dwarf physics, better chronometer samples, better control of the local distance ladder, better gravitational wave standard sirens, better high redshift observations, more precise BAO maps from deeper surveys, more careful assessments of systematics. Some numbers may shift slightly, uncertainties may narrow, certain tensions may soften or sharpen or resolve into new categories. But it would take something far more dramatic than ordinary refinement to erase the central conclusion that the universe is ancient on the order of 13.8 billion years, and that we know this through a remarkably rich combination of evidence. That, in a way, is the deepest comfort in the file. The answer is not fragile. It does not depend on one exotic machine or one temperamental dataset. It depends on the fact that different corners of physics, observed across different scales and times, agree on a vast duration. The universe is old enough for long cooling and long drifting, old enough for stars to be born and die and leave compact remnants, old enough for galaxies to assemble, old enough for clusters to orbit quietly in halos, old enough for light itself to cross nearly all of cosmic history and arrive here faint and cold and still legible. Outside the window, distance remains what it has always been, not empty exactly, but occupied by light in transit, by old records still on their way. The folder on my desk no longer feels like a question with no handle. It feels like a patient answer. The office, with its shelves of older notes and its lamplit desk in the present, has turned out to be a decent metaphor after all. To find the age of the universe is to work backward through the room, from what is nearest to what is oldest, from the visible desk to the dimmest shelves, until the arrangement of everything tells you how long the room has been filling. The mug beside me has gone from steaming to merely warm. The ribbon of vapour is gone now, but the thought of it remains. Something visible for a little while, fading in a way that still reveals motion, direction, and time. That is all an age measurement really is. Not a glimpse of the beginning itself, but a fading trace from which the duration can be inferred. And so, at the quiet end of the file, we can say it plainly. The universe is about 13.8 billion years old. We know this not because the cosmos offered a single confession, but because expansion, light, stars, remnants, elements, and ancient objects all gave statements that, when compared carefully, belong to the same long story. And now, at last, we can close the case file, set the folder gently back on the desk, and let the age of everything rest where it has always rested, all around us, carried softly in the oldest light and the oldest clocks, still ticking, still cooling, still crossing the dark